Okay. Tests are being graded. I forgot to bring my 50-cent little doohickey that goes on the end of this thing, so it's going to be at a weird angle. And if I bump it, then it will be off center. That's okay. I've got other videos. What we're going to talk about today is light. We're starting the third phase of 214, the sixth phase of pre-med physics, the last phase of physics that you'll ever take. Yay! We should all be grateful for that. So, in this particular chapter, we're going to talk about light, talk about some of its weird behavior, and get this thing fixed. All right. So there's a particular chapter that we're just going to briefly touch on. Light is weird. Light has the idea of particles, and you could treat it like what they're called are photons. Photons are just little itty bitty bits of light. The light that you see right now is the culmination of just a ton of photons entering your eyes, interacting with the cones and rods. See, I know biology. The cones and rods of your eyes, and then those create electrical stimuli that go into your brain. The other thing is light is a wave. And we're familiar with waves because we've kind of studied them in fluids, and we've studied them in springs and in air and all sorts of things. And when we look at light, we look at how the parallels between fluids and sounds and all that stuff, and how does this work on what we're about to study. With light, it is, and this is the time, if there's ever a time you're going to buy like a ruler and some pretty colors, pens and pencils, now's the time. Now, ideally what that's supposed to be is in the horizontal. We have an electric field wave where occasionally the electric field is kind of into the page and other times it's out of the page, and it sits there and it oscillates. And in the vertical, it's B, and what I'm going to do is draw another wave. Now there are much better pictures out there. To do this on the fly is a little bit difficult. But if you were to look at this, it's a badly drawn picture because it looks like it's just like a DNA strand. But in the horizontal, you have the electric field oscillating back and forth, and in the vertical field, you have the magnetic field oscillating back and forth. And this is the idea of an electromagnetic wave. An electromagnetic wave comes in all sorts of forms. You've got light sitting there in the middle. And then on one band, you've got like the ultraviolet. And the other side, you've got the infrared. And what ends up happening is that you got one side has higher frequency and the other side has lower frequency. And there are all other types of light. When you get up to a particular, like you've got radio waves, all sorts of things where it all follows this behavior, that the velocity of the wave is equal to the wavelength times the frequency. Now we'll go back to standard view. Now, one of the things that they don't tell you, I just do it because it just kind of makes sense, is there is a function, you guys don't need to know it, but it's just for your benefit. S is E cross B. Now, S is what they call the Poynting vector. And yes, it's spelled like that. And what the Poynting vector is, if you go, all right, I know my E field, I know my B field. Which way is this wave going? You go E cross B, that's the Poynting wave. And so you end up with horizontal is the E. Well, in this particular case, they're going that way. And so you can tell the direction of the wave merely by the alignment of how the E fields and B fields oscillate. Huh? Do you need to know that for a test? No. I just say it just because we're here to educate. Sometimes I don't test the stuff that I say about. Like, you've never been tested on how much I dislike certain pop stars. Doesn't prevent me from talking about it. So now, this is a particular identity, velocity, or equation that we really need to know. Yes, Richard, you will be tested on this. Because I say so. Because if you say why again, I'm going to fail you. So now, for most cases, in a vacuum, this V is equal to C. That the electromagnetic wave is traveling at the speed of light, and so C is equal to lambda F, and C is equal to 3 times 10 to the 8th meters per second. And so that's the speed of light. Nothing can travel faster than that. Occasionally you get a scientific group that thinks that they can beat it, but so far Einstein has been pretty spot on with this. Now, light, when passing through material, slows down. Not gown, down. And in fact, when it passes through air, it slows down a little bit. Really what's happening is that the material is absorbing the light and re-emitting it. And what this does is this absorption and emission effectively slows down the material, or it's the light passing through. And the ratio of C over V, where this is the speed of light in vacuum versus the speed of light in material, that this C over V is called N. And that is index of refraction. Now, the index of refraction for a vacuum is 1. If you take C and divide it by itself, you're going to get 1. Yes. What the pointing vector is doing is it's just giving you the direction in which it's headed. Go ahead. I would say yes. Yes. Like yes. It's also something, don't worry about it. Well, and this goes into the whole thing, the question of physics for 213 and effectively for 214. It's very nice. It's very coherent. But then there are things on the fringes that makes you start wondering, stuff's getting weird. And if we were to start talking about like quantum mechanics, Heisenberg's uncertainty principle, there are higher level things where physics goes from it has to be this, it's this number, to if you think I'm bad about alphabet soup notation now, take a quantum mechanics course and the whole thing just falls apart. It moves from things that are certain to things that are probability. And it just gets odd. So the answer, yes, please don't ask any more like that, because it just confuses the rest of the people. Now, N for air is effectively 1, and as far as I'm concerned, the index of refraction for air is 1. Speed of light in this room is effectively 3 times 10 to the 8th. Now, technically, I think it's like 2.999999. It slows down an itty bitty bit, but it's not enough to affect anything. The one thing that I will say is that all n's must be greater than or equal to 1. Yes. What is the what? Huh? In back. Yes. Now this is I enjoy the fact that it provides us with cool air, but it also makes hearing difficult. Especially probably for the people back in the back. This, greater than or equal to 1. All. A-L-L. Ugh. All right, I'll have to write bigger. And typically for like glass, it's about equal to 1.5 N of water, 1.33. For these types of materials, the bottom line that you have is, well, what are we going to be tested on? What value is it? I'll either ask for the value. Typically my generic value for water is 1.33. I think that's what it is anyway. Glass comes in all types of flavors. So it could be 1.4, 1.5, 1.8, whatever. We're going to start reintroducing, or we're going to reintroduce rebellium. Yes. If I invent a new element, I will call it rebellium, and then I will tell everyone else to go away. Rebellium is my fictitious element whose properties are whatever I want it to be at the time. Is it a gas? Is it a liquid? Is it a solid at room temperature? Yes. That's how we roll. Now, in a vacuum and in generic material, there are differences. For a vacuum, the N is equal to 1.0, etc. For a material, N is greater than 1.0. In a vacuum, the velocity is equal to c, which is equal to 3 times 10 to the 8th meters per second. For a material, the velocity is c divided by n. So that velocity will be less than 3 times 10 to the 8th meters per second. And when you look at the sample test 3s that will come out, this particular thing that I'm working on right now is about 5 to 10 multiple choice questions. Now there is something, well, it's the wavelength, it's the distance between the waves, and that is c divided by f, where f is the frequency, and then lambda prime is equal to lambda divided by n. So the lambda in a vacuum, and you can also get it by that. The wavelength of a vacuum is the speed of light divided by its frequency. It's whatever frequency of light we're talking about. Light has a particular frequency, infrared has a particular frequency, ultraviolet, radio waves, stuff like that. But in a material, the wavelength changes. But the one thing that doesn't change is frequency. Frequency of light remains a constant regardless of the material. So the frequency of light remains a constant regardless of the material. So red light in air, it's going to be red light. How do you determine the color? Really, it's all based on the frequency. The frequency of light in air is the same as it is in a vacuum, which is the same as it is in glass. So if you've got something like, I forget, like 8 times 10 to the 14th hertz light, and it enters glass, what is its new frequency? It's 8 times 10 to the 14th. And you're hearing me repeat this, so as your private tutor, did he say it 3 times? Well, not yet. Frequency doesn't change. That's the 2nd time. So he hasn't said it 3 times. Frequency doesn't change regardless of the material. Oh no, he said it for the 3rd time. So if you get into the test and you say that the frequency of light changes, I told you 3 times. What else do you want me to do? Now, one of the questions that you can ask is, why doesn't it change? Frequency, and of course people are going to start rolling their eyes, due to quantum mechanics. See, I can't even spell mechanics right. That's how messed up I am. Light has all types of energy. The higher the frequency, the higher the energy. It is a quantum mechanical modern physics requirement that the frequency of the light is based solely on the energy of the particle. The energy of the particle doesn't change regardless of the medium, therefore the frequency does not change. Or, from a 214 perspective, frequency ain't changing and I don't care why. For those of you who are curious, it's a quantum mechanical thing. It's some heavy stuff. So never change it. Let's say, for instance, I've got, well, I got to introduce one last thing. We're familiar with meters, millimeters, micrometers, nanometers. Meter is 1 times 10 to the negative 3 meter, 1 times 10 to the negative 6 meter, 1 times 10 to the negative 9 meters. And that's really small. And now traditionally, light is on the order of, oh, please, let me get this right. Oh, if anybody had the book, but none of us do, so why do we even bother? Hold on, let me get it. I don't think I'm gonna have this. I wanna get the numbers right. Google the wavelength of red. I think it's like, I want to say it's like 600 nanometers. But I'm probably wrong. Huh? If we only had calculator girl, guess she was up too late watching the basketball championship. All right. The other unit, while we're looking it up, is this. It's called an angstrom. A-N-G-S-T-R-O-M. Angstroms. Do that again. 650 nanometers. All right. So red, 650 nanometers. An angstrom is 1 times 10 to the negative 10th meter, or 10 angstrom is equal to 1 nanometer. And when you're down in the range of optics and atomic physics, now angstroms becomes kind of important. 10 times 10 to the negative 10th meter. So we have, let's say, red light in a vacuum. I want velocity, I want, let's do the dumb ones. Well, that one is obvious. It's C, which is equal 3 times 10 to the 8th meters per second. Index of refraction, well, that's dumb. It's 1.0. That's the index of refraction of a vacuum. Let's get interesting. The wavelength is equal to 650 nanometers. So the frequency is what? Well, what we use is V is equal to lambda f. Now, one of the things that you could sit there and go, and even I look at this and go, I have no idea if is V equal lambda f, lambda over f, f over lambda, is FV equal lambda? I'm just confused. Remember, units won't lie to you. What are the units of velocity? Meters per second. What are the units of lambda? Meters. What's the units of frequency? Hertz or inverse seconds. So V is equal to lambda f. So V over lambda is equal to f. So 3 times 10 to the 8th divided by. Now for this, you do have to change this into meters. Lambda is 650 nanometers, or 650 times 10 to the negative 9, and that gives us a big number. Yeah, if only I can hear you. 4.62 times 10 to the 14 hertz. And that's the frequency of red light. Yes? Well, right now we're dealing with just a vacuum. So the velocity in this case is c, because we're in a vacuum. We haven't gotten into a new material yet, but in the next 60 seconds we will. So this red light passes into glass. Its new velocity is 2 times 10 to the 8th meters per second. What is the index of refraction? So that's the first question. Now, a lot of this, I could give you the index of refraction, or I could give you the velocity, or I could give you the new wavelength. The index of refraction is defined as the ratio of C over V is equal to N. So this is 3 times 10 to the 8th divided by 2 times 10 to the 8th. So it's equal to 1.5. Now, little short story about my 213 students. We had our energy test, and one of the questions that I asked was, what was the fraction of energy remaining for this Atwood's machine? I know an Atwood's machine on a test, I'm shocked too. That never happens on a 213 test. And one of the things that really tripped them up about was, well, what are the units? I'm like, what do you mean, what are the units? And they said, well, what are the units for a ratio? For an energy ratio? Do we just use joules? And I'm like, it's a ratio. Therefore, it has no units. So what are the units of an index of refraction? Nothing. There are no units. You've got velocity over velocity, which means there's nothing. Next. What's the new frequency of the light? What is it? It's the same, exactly what I've been ranting about before. So you just immediately write 4.62 times 10 to the 14th hertz. Done. Next, what is its new wavelength? So this can be done a variety of ways. You can use V is equal to lambda prime f, the lambda prime always already takes into account the index of refraction. You could write C over N is equal to lambda prime f. But that's kind of, you can do it either way. But since I already have the velocity in this case and I have its frequency, I'm just going to use this one. Lambda prime is equal to v over f. The v is 2 times 10 to the 8th. The wavelength is 4.62 times 10 to the 14th. And I get a lambda prime of 4.33 times 10 to the negative 7 meters, or you could write 433 nanometers, or 4,333 angstrom would be right either way. Yes. Oh no, Adrian's just wiping her eyes. So that's some of the behavior of light and how it passes through different materials. Now, light, what you guys are doing is, it's not, what's the name of the geometric optics? Now, next week, which will probably be the subject of Thursday's lecture, we're going to be dealing with lenses. But today, we're going to deal with mirrors, just some straight up stuff. For geometric optics, we initially have the law of reflection. And the law of reflection this is our normal line. Normal line as in normal force. Normal is perpendicular to the surface. The law of reflection, now if I brought my handy dandy compass or protractor, on the test, for test 3 and the final, you will be allowed to bring a compass or a protractor and a ruler. This is my favorite ruler. I've bought tons of rulers. I've bought the aluminum ones, the steel ones, wooden ones. This I love because it's clear. You can see what's directly underneath it. It's wide and just, I'm not making any money from this. After a long type of study, this is it. Yes. Is that answer? All right. And now granted, I can look at these lines and go, this looks horrible. But the law of refraction or reflection says that theta sub I is equal to theta sub R. This is the incident angle. This is the reflective angle. So the law of reflection, pretty obvious. Incident angle is the same as the law of, or as the angle of the reflective angle. Blah. Now, if you have a mirror so this is the front of mirror. This, no, I take it all back. The way that I drew it. That's the back. That's the front. You've got well, that's the normal for one. But if you put something like a pen here, the light that, and actually I'm going to put a second pin here. The light coming from these pins hits the mirror and reflects. And what you're going to do is you're going to put your eye at a particular location. Now all of this is happening, there's a mirror on a cork board, you put 2 pins on the cork board, and what you're gonna do is you're gonna look and you're gonna place 2 pins here that line up with those 2 pins there. And now you can also do this. And actually what I'm going to do is, I'm going to change this up a bit. There's only 1 pin because we're going to need multiple angles. What you do is you look at the pin in the reflection and you put 2 pins that block that pin in the mirror. So these pins in the mirror. And there is, you can also do it again so you're going to place another 2 pins, and what's going to happen is you're going to take the mirror off the cork board, and then you're going to line it up with the dotted lines of this. And so you're going to end up with this is your virtual pin. And what you should discover is that that distance and that distance are equal to each other. Now in reality, it's not going to match up. Why? Because you guys are just first year physics students, and we're not asking for perfection here. But what we are asking for is that you're able to identify that light from these 2 rays effectively line back up to where that pin's virtual twin is. And so this is what we would call a virtual image. And it's also a demonstration of the law of reflection. Now, Let's see what, and they also call it the parallax method, but I just like lining up some pins. Now, what they're gonna do is this pin particularly here, is one of 3 pins in a triangle. So you're going to have, this is the pin that we just worked with, and there are going to be 2 other pins because they're going to give you a triangle and you're going to mark them off. And then you do this parallax method where you just line up pins and you create another triangle. Now, in a perfect world, this triangle and that triangle will all have the same lengths. It should look like a triangle. It's going to have 3 sides. The sides are going to be slightly different lengths because of error, but it should be about the same. Can you, using this parallax method? Oh my goodness, I've gone nuts. You should be able to create another triangle on the other side. Let's see. And really all I'm doing is just kind of looking at the notes that they're going to be showing you today. Reflection. With the law of reflection, huh? All right, this one's really unnecessary. In the law of reflection, you got the mirror. This is where you're going to have the 2 pins. You're going to simulate a light wave. You're going to have 1 pin and then another pin over here. And so the light from both of these are going to go in this direction. Now what you do is you place two pins where you're looking at it these 2 pins block the images of those 2 pins. So when you look in the mirror, because the mirror is only going to be like a few centimeters tall. You're going to have your 2 black pins reflected in the mirror. Oh, this is a horrible picture. Actually, no, it's not going to matter. If you look in this particular way, you're going to see these 2 on that side, and all 4 should block each other. And what you're going to do is you're going to measure that angle, you're going to measure that angle, and you're going to show that theta I effectively is equal to theta R. And so that's all you need for that part. We got reflection, refraction. Okay. Now, refraction. In uniform situations, all air, all glass, etc. The shortest distance between 2 points is a straight line. So if you have a point there and you have a point there, the shortest distance is from there to there. Fairly easy. Now really what we're asking ourselves is, now why are we traveling from there to there in a straight line? Well, it's the most efficient way to get there. It actually takes the shortest amount of time to get there. And what this starts introducing is the principle of least action, sometimes referred to as least time. What's more important is the path of shortest time between 2 points. It's a straight line. So between 2 points, if you're in a uniform medium, if you're entirely in air or water, or if you're walking on a beach or you're walking on a lawn, if you've got 1 point you need to get to and it's all on a lawn, then you just walk straight to it. Not very difficult. But in situations where two mediums are involved, the path of least time is not a straight line. So what does this, how do we demonstrate this? Well, let's say for instance, you are a lifeguard. And here is ocean, and here is beach. Now you are there, and then over here is a basket or a sinking basket of puppies. Now there's a story behind this. I don't choose puppies because I like being cruel to puppies. I chose a sinking basket of puppies to get attention to the class. Originally, the first time I ever did this, I said Justin Bieber was in a basket and it was sinking. Go save Justin Bieber. And the class collectively said, no, let him drown. So I had to make it a little bit more interesting, and I go, okay, fine, whatever. Basket of puppies, save the puppies. And they were like, okay, now we can go and save the puppies. So you've got to pick the best way of getting to the basket of puppies in the least amount of time. Now you could choose the straight path, but what that does, it's not efficient, because the ocean, in the ocean, the velocity of the ocean, you're slow. You swim more slowly than you can travel in sand. You're faster on land than you are in the ocean. So there are not very wise ways of traveling. There's this way, where really you're just you're running immediately into the beach, you get down to even with the basket, and then you travel that way. This is hideously slow and long. You could go, well, I'm gonna travel as much as I can on land and then cut down and head towards the puppy. But even then, you're spending a lot of time on land. So the truest way of doing this, the best way, is to kind of spend a lot of time on land, but not all the time. And then once you come in contact with the medium of the water, you turn into it. This is your optimal path. So light, or people, in order to get from one point to another in the quickest amount of time, actually travel a longer distance than the optimal, the shortest path, shortest length. And what's really interesting is I'm about a year after I taught this to a particular student, she came to me and she said that they were playing like soccer or something, and she was here and she was walking on grass, and well, let's just draw it out. So here was grass, which is slower than the parking lot, which is asphalt, because the grass was taller. And she was here and her car was there. So what she did is she kind of lowered the amount of time that she was walking on the grass, and then banked left to her car, because the velocity of the parking is greater than the velocity of the grass. And as she was doing this, she said, oh my goodness, I'm doing physics. So it does exist. I mean, granted, there's no shame in just walking straight towards the car. But if you wanted to take the least amount of time to get to your car, you're gonna kind of have to bank it. Spend a lesser amount of time on the grass and more amount of time on the asphalt, just as you would want to spend a little more time on the beach and a little less time in the ocean. Now, there is a relationship between these two. And really what I'm gonna do is, I'm gonna change this from vacuum to glass. Index of refraction of glass is 1.5. And I'm going to ask for the relationship between the angle of refraction and the incident angle. When you're dealing with this stuff, because the indexes of refraction are different, you cannot assume that the angles will be the same. The angle of reflection is not the same as the angle of refraction. Reflection, it's just bounced. Refraction, it's bent. For this, you need to understand Snell's law. For Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. That gives you the relationship between the index of refraction and the angles. And when you're all meditating on it, I got to see if I got to cover. What if the if this was in a straight line? Well, if it was all lined up like that, then it would be the same material. It wouldn't bend at all. And in fact, when oh, I do have to cover it. 13 minutes. We're going to do this. Yes.
In Snell's law, is it theta 2?
Oh, I'm sorry. 1. Thank you. On the lab today, what you're going to do is you're going to line up 2 pens, and you're going to go and on the other side you're going to line up 2 other pens. Now, what's really weird about this is that when you look at these 2 pens, these 2 pens line up with these 2. So when you look at these 2 within the glass, you will see the other pens. Now, when you look above the glass, the pens will be in different places. But when you look in the glass, they'll be in the same place. And really what's happening here is that the light is refracting. And in fact, what I'm going to do is I'm going to draw it a little bit more obscene and these angles here are going to be the same. These angles here, I'm going to call theta R, and the other ones theta A for air. The light comes in and it refracts inward due to Snell's law, and then it goes back out doing its own thing as originally. So these theta A's and theta R's are the same. Now what you're going to do is, you know the length, you know this length here, and you can calculate this angle here, and you will be able to measure all the angles such that sine theta of air divided by sine theta of r is equal to the index of refraction. So you'll be able to calculate the index of refraction of the material from this. So you sit there and you draw everything out, you measure the angles, and you can get an approximate angle for, or I'm sorry, approximate value for the index of refraction. All right. The last bit that we're going to talk about is total internal reflection. What happens to what? Oh, in air, why'd that go away? Good question. N of A is 1. So it just goes away. So for the last part, what you will notice is you get a, they're going to let you hold little pointer lasers, and you're going to fire your laser into this, and then the laser light will come out there. And this is just that smoky quartz. Not quartz, quartz. Light under certain circumstances today is not a good day for me. Oh, that's definitely bad. All right, let me move that over here. So light under certain circumstances will reflect. Now, if you just have, let's say, air and water, if you just have a ray of light here, the light will go straight through. If you move a particular angle over, that light will bend even more. If you are at an even steeper angle, the light will reach a particular, or will reach the point where the light is traveling parallel to the surface of the water. This is the theta C, or critical angle. And then if you go any steeper, it reflects. Light will bounce off the water. If you're looking, perfect example, if you're looking, go to the pool in Turner Center, when you look up, you could see directly above you. But if you look over to the angle, at a particular angle, the surface of the water looks like a mirror. It doesn't show you any of the light that's above it, only the light that reflects up from below. So what happens is that at this critical angle, so if the incident angle is less than the critical angle, it refracts. And you do Snell's law. If the incident angle is equal to the critical angle, what happens is that the angle of refraction is equal to 90 degrees. And if the incident angle is greater than the critical angle, you have reflection. And the incident angle is the same as the reflected angle. So you need to understand that light has a particular behavior when it's reflecting off certain mediums. The one thing, and what we're going to do is we're going to stop now and or answer this one question. Yes.
So in your pool example,
Yeah.
you go over and look at that critical angle. What
Basically, you just see like you would see infinity. No, it's really really what's happening is it just goes from the ability to see to mirror. And so I guess what you see is the edge of the mirror. It's the boundary at which, I know, it's the boundary at which it changes from a mirror to passing through. I haven't really, yeah, that's it. All right, class over.